ready to deploy LSAM for orbital test.
In frigid, silent darkness a million miles from Earth, an immense space telescope scans the heavens. Shielded from the sun, Earth, and moon, it pursues profound mysteries. How do planets form? How did matter come together to make the first stars and galaxies? Where among the stars might we find life? Astronomers worldwide will seek answers using the unprecedented capabilities of the Webb Space Telescope. Telescopes work best from dark locations above as much of our turbulent atmosphere as possible. A telescope above it all can see much finer detail and capture invisible colors of light that are blocked by the atmosphere. Beginning in 1990, we deployed a series of great observatories into space, making discoveries that have revolutionized our understanding of the universe. But these pioneering space telescopes have limits. Spitzer's modest mirror size means it cannot resolve fine details. Hubble cannot see far into the invisible infrared. With its enormous mirror, Webb will gather 60 times the infrared light that Spitzer can, and will see as sharply as Hubble. Webb's design is driven by astronomers' need for a next-generation infrared observatory. Infrared is key to penetrating dusty shrouds where stars and planets are born, and to capturing the light emitted by the earliest stars and galaxies. Coated in gold that reflects infrared light, Webb's light-gathering mirror segments are made of the exotic element beryllium, which maintains its shape at very low temperatures. Light reflected by the mirrors is focused to cameras and spectrographs behind them. Layers of reflective insulation stretched across an area the size of a tennis court form a sun shield that protects the telescope from the intense light and heat of the sun, Earth, and moon. The telescope must be kept at 40 degrees above absolute zero, or its own infrared glow will overwhelm the faint sources of light that astronomers are trying to observe. On the hot side of the observatory, solar panels make electricity from sunlight, and radio antennae communicate with Earth. In space, Webb will loop around a point called L2. Here, Earth's gravity pulls the telescope along so it can keep up with Earth in its path around the Sun. Only from L2 are the Sun and Earth always on the same side of Webb's sunshield. An Ariane 5 rocket contributed by the European Space Agency will launch Webb into space. During its voyage to L2, the telescope will unfold like a flower. And then begins a decade-long bonanza, the best science proposed by scientists in competition around the world. We have found hundreds of stars that have one or more planets in orbit. There are probably billions of planets in our galaxy. Are any suitable for life? Hubble and Spitzer have shown that the answer may lie in studying systems where a planet passes directly in front of its star, illuminating the planet's atmosphere. Beginning in 2009, NASA's Kepler mission will begin to discover planets by the thousands, watching stars dim by tiny amounts as unseen planets pass in front of them. Webb will investigate many of these planets. Scientists will be able to detect life-supporting chemistry and examine temperatures of planetary atmospheres and surfaces. We will better understand whether habitable conditions exist beyond Earth. In our solar system, small rocky worlds orbit close to the Sun, gas giants farther out. But around other stars, we're finding Jupiter-sized planets in Mercury-sized orbits, in part because they're the easiest for us to find. Is our solar system an odd one, or are systems like ours waiting to be found? For clues, we look to disks of dusty debris circling newly formed stars. Around the star called Fomalhaut, Spitzer sees a ring of warm dust, and Hubble finds evidence that a giant unseen planet has been sculpting the ring. Webb will show us giant planets within debris disks and detect invisible planets by how they affect their disks over time. We will learn whether solar systems like ours are common or rare. To look far into space is to look back in time. In 1995, Hubble showed us galaxies as far back as 1.5 billion years after the Big Bang, the explosion that started it all. In 2004, the Hubble Ultra Deep Field pushed the frontier back another 500 million years. Webb will show us light from galaxies in their infancy, 13.5 billion years ago. We will be able to see how light from the very first stars heated the gas in the early universe and made it transparent. And how galaxies, so odd-looking at the beginning, evolved through gentle growth and titanic collisions. Webb is more than a dream. It's a dream coming true. The beryllium mirror blanks have all been made and are now being polished. Fine mirror control mechanisms are being tested. Cameras and spectrographs have been designed and are under construction. By 2013, the Webb Space Telescope will be ready to fly. On the day it does, a brand new adventure of scientific exploration begins.
The Webb is going to be such a powerful telescope. It's going to be like the Hubble. And in the case of the Hubble, probably more than half of the greatest observations, discoveries that the Hubble made were things people didn't anticipate. I expect the same for the Webb.
We have a telescope that's far more powerful than anything that we have had before, working at infrared wavelengths, which you can't see well from the ground. And that will enable us to see things from the most distant universe that we can only guess at, things in the outer solar system that we can only guess at.
The Webb will be wonderful for the astronomy community. Not only will it give them the kinds of wonderful resolution we have with Hubble that you can get above the atmosphere, but it's going to bring them access to a wavelength region where many of them have not worked before.